Today, we're going to embark on an exciting journey through the cosmos as we delve into the laws that govern the motion of celestial bodies. Welcome to Gravitation and Orbits, Kepler's Laws. Kepler's first law, also known as the law of ellipses, states that the orbit of a planet is an ellipse with the star at one of the two foci. When we previously discussed the forces and fields of celestial bodies, we did so using the simplified circular orbit. However, in actuality, celestial bodies orbit in ellipses. It was Johannes Kepler who first formulated that planets actually orbit the Sun elliptically, kind of a squashed circle, if you will, with the Sun not at the center as you may expect, but rather at one of the foci, which, for our purposes, will just be thought of as two offset reference points, equidistant from the center. Some celestial bodies like Earth and Saturn have elliptical orbits that are almost circular in shape, while other objects like comets can have very elongated ellipses as their orbits. Kepler's second law, the law of equal areas, states that a line joining a planet and the Sun sweeps out equal areas during equal time intervals. As an example, as this planet sweeps out the black area in some amount of time, at any other point in its orbit, it will sweep out the same area in that same amount of time. Therefore, all of the black areas that are being swept out are equal. And the law says that if we do that anywhere else, as long as the time interval is the same, the area swept out will also be the same. Kepler's second law can be extrapolated to show the conservation of mechanical energy. When a planet orbits a sun, as it gets farther away, it slows down, decreasing its kinetic energy, but increasing its gravitational potential energy. And conversely, as the planet nears the Sun, the gravitational field accelerates the planet, increasing its kinetic energy while decreasing its gravitational potential energy. Kepler's third law, also called the law of harmonies, states that the squares of the orbital periods of the planets are directly proportional to the cube of the average of the maximum and minimum orbital distances. In equation form, t squared is proportional to r cubed. The application of this law shows that the farther a planet is from its star, the longer it takes to complete one orbit around it. This law can be derived by using the assumption of a circular orbit and combining Newton's law of gravitation and Newton's second law of motion in its centripetal force form. Starting with Newton's law of gravitation, we know that the gravitational force in this equation is the force between two masses, a sun and a planet, for example. This gravitational force acting on the planet is also the centripetal force responsible for keeping the planet in its orbit. Mathematically, we express this relationship as F equals m times v squared divided by r, where m is the mass of the object in centripetal motion, v is its orbital velocity, and r is the average radius of its orbit. By equating the gravitational force to the centripetal force, we get the gravitational constant times the mass of the star times the mass of the planet divided by the square of the orbital radius, which is equal to m times v squared divided by r. Notice that the mass of the object undergoing centripetal motion cancels out, and so does one of the r's, simplifying the equation. Now, the speed of an object is just distance divided by time. In terms of circular motion, the distance is the orbit of the object in circular motion, 2 pi r, where r is the radius of the orbit. This happens in one time period t, and therefore the orbital velocity is 2 pi r divided by t. Substituting this expression for v into our equation, we get g times m divided by r is equal to 4 pi squared r squared divided by t squared. Don't forget to square all the terms, as so many students do. Moving all of the constants over to the side with the t squared, we see that gmt squared divided by 4 pi squared is equal to r cubed. The term gm over 4 pi squared is a constant that depends on the mass of the body being orbited. This means we have the period squared is proportional to the radius cubed, or Kepler's third law, which again is that the period of a planet's orbit squared is proportional to the cube of the distance to the celestial body that is causing it to remain in orbit. So, that wraps up our discussion on gravitation and orbits, with a closer look at Kepler's three laws of planetary motion, including Kepler's law of ellipses, the law of equal areas, and the law of harmonies. These findings were pivotal in revolutionizing our understanding of the cosmos, setting the stage for Isaac Newton's groundbreaking work on the laws of motion and universal gravitation. We've also seen how Kepler's third law can be derived using Newton's laws, further deepening our understanding of celestial motion. Thanks for watching.